Hi from the IT department. So welcome to the Open Innovation Lab. And we will have weekly meetup like this. And we will post the events in Facebook. So if you like us and want to join, want to know more events, just join our group. And today we will discuss the Bitcoin and the smart contract. Actually, I'm quite interested in these two topics. And we will first have Yongxun. He is a security PhD student in this cryptography, and he will introduce the Bitcoin for us. And later on, we will have Carson. He is another curator member of this oil. So later on, we will have some demo. And if you want to also do something, you can download this VM from this address, or you can ask for the USB. And this is the Wi-Fi information. Okay, so I will hand the time to Yongxun.
Okay. Thanks, Yonghai. Thanks for inviting me to give this talk. So a little bit more information about myself. My name is Zhao Yongjun. I'm a PhD candidate in Information Engineering Department, supervised by Professor Sherman Chow. My research is mainly on cryptography, especially on privacy-enhancing technologies and protocols. Bitcoin interests me for a long time, but Bitcoin itself is not my research topic. So I was honored to be invited by Yonghai, so he gave me a chance to pick up Bitcoin and really look into the details of Bitcoins so that I might have a better chance to do some research on it. And during this talk, I will give you some information about how Bitcoin works from a cryptographic viewpoint. And during the course, I will introduce some important crypto tools that are that is very essential for the security of Bitcoin. And I hope during our interaction, all of us will learn more about Bitcoin. Okay, just a little bit history about Bitcoin. In 2008, someone posted a white paper on the internet under the pseudonym of Satoshi Nakamoto. In this paper, he or she described a protocol called Bitcoin, which is a decentralized cryptocurrency. A few months later, in early 2009, the first open source Bitcoin client was posted into the internet, and at that time, the first few Bitcoins were created, and then things start to work slowly. In the first few years, actually, the infancy of Bitcoin, it does not cause much interest from the general public or research community. But somehow, starting from 2011, some merchants start to accept Bitcoin as a real currency, and later on, it somehow attracted more attraction from the general public and also from researchers. And by the end of 2013, the price of Bitcoin skyrockets. You will see a picture showing how the price goes up and down in the next slides. And because it has attracted so much attention, something happens. For example, some exchange got hacked, and due to the hack, such an exchange point have to shut down, and some governments start to impose some regulations on Bitcoin, saying that whether Bitcoin is legal or not, and things like that. So this is the Bitcoin exchange rate, Bitcoin versus US dollars. You can see that at the beginning, Bitcoin does not worth too much money, but somehow at the end of 2013, the price goes up very high. And then it drops down because countries start to pose regulations so that people start to fear that Bitcoin does not worth anything, and then the price drops down drastically. And recently, the price somehow goes up again. We don't know how the trend will be, but this is a little bit of information that I think is useful. And here's another figure showing the number of transactions, the number of Bitcoin transactions per day during the early days of Bitcoin to recent months. So you can see that the number of transactions is actually increasing very steadily. Okay, the goal of this talk is to informally introduce some major crypto tools that are used in Bitcoin. In particular, we only introduce two important tools. One is cryptographic hash, and the other one is digital signatures. And after that, I will go into a little bit details about how Bitcoin works, especially how it achieves decentralization, and what is the blockchain in Bitcoin, and what is Bitcoin mining, things like that. And during the course, I will also discuss whether Bitcoin is secure or not. Okay, this is the outline of today's talk. So let's start with a little bit of cryptography. So the first tool that I want to introduce is cryptographic hash functions. This is just some function that takes arbitrary length input. What is special about hash function is that it outputs a fixed size. The output is fixed size, usually 128 bits or 256 bits. It is also called a digest because it somehow compressed arbitrarily long input into some concise representation of that input. It is required that hash function should be efficiently computable, namely, the function should terminate in a reasonable amount of time. Without any security properties, then hash function will not be of any use. So in cryptography, we assume that hash functions have the following properties that are especially useful in Bitcoin. And I will not define these two properties in a formal manner as in cryptography, but I will give you high-level intuition about what these properties mean. The first property for a cryptographic hash function is so-called collision resistance. So what do I mean by collision resistance? Let's say the hash function takes input, arbitrary length input, and outputs an n-bit string. Let's say it is a cryptographic hash function. Then we define a collision of this hash function, be a pair of distinct inputs x and y, such that once you feed it into this hash function, the output will be identical, namely hx equals to hy. Then we call this pair of distinct inputs as collision. We say that a hash function is collision resistant if it is computationally infeasible to find a collision. So notice that the input space of the hash function is very big, much bigger than the output space. But somehow magically, that implies that there must be many collisions. There must be many collisions. But somehow we just don't have a feasible way of finding any single one of any single one of collision. This is some magical property that we expect for any reasonably secure cryptographic hash functions. One useful application of such a property is that we can use the result, namely the digest of a file, to represent the file itself. The file could be very long, say gigabytes long, but its representation, namely the digest, could be very short, for example, 256 bits. we only, to remember that large file, we only need to remember that short hash. And because we assume the hash function is collision resistant, that means it is hard to find another file that would result in the same hash. So we can use this short information to represent the potentially very long file. Okay, this is the first property of cryptographic hash function. The second property is called puzzle-friendly. This property is somewhat non-standard from a cryptographer's point of view, but it is named because of its usage in Bitcoin. So puzzle-friendly says that for every possible output value y, we split the input of the hash function into two parts. The first part, we call it k, the second part, we call it x. If the first part is chosen from a distribution with high mean entropy, namely this, in this distribution there's no single value that takes particularly high probability, then it is impossible to find even a single x such that the hash of the concatenation of k and x will equal to y. Of course, you can always try every possible values. You vary it and you try any possibilities. Eventually, you will find out such an x that will result in y. But the puzzle-friendly property states that this is the only way you can find such an x. So just to repeat, puzzle-friendly property says that the only way you find an x such that h of k concatenation with x will equals to some target value y. The only reasonable algorithm is just to try every possible value of x. If you have any questions, you can stop me at any time and ask me questions. This property seems a little bit weird, but in fact this property is especially useful in Bitcoin, especially in Bitcoin mining and blockchain extension. So one immediate application of this property is that we can define something called search puzzle in the following way. So the puzzle works as follows. So we choose an ID of the puzzle from some high mean entropy distribution, namely you specify the ID of the puzzle here, and a target set y. The puzzle asks you to find a solution x such that hash of the whole thing falls into this target set. And if you are careful, you will see that this property is almost exactly as the puzzle-friendly property of Bitcoin puzzle-friendly property of hash function I just introduced. And because of the puzzle-friendly property, we can conclude that there's no solving strategy for this puzzle that would work much better than just trying random values of x. So looking a little bit, looking ahead, this kind of search puzzle is very similar to the one that is used in Bitcoin mining. Okay, having talked about hash functions, then we take a look at some immediate applications of hash functions. So here we introduce a new data structure called hash pointers. So hash pointer is pretty much like linked list that you have learned in your data structure course. So it consists of a pointer to some data and If this data structure only contains this data and this pointer, then it is the linked list we learned in computer science course. But what is special about this data structure is that it also contains a hash of this data. So it contains a pointer and a hash of the data it points to. So the nice property of this data structure is that it has a way to retrieve the data it points to because of this pointer. Also, because of this digest of the data, it has a way to verify integrity of the data. Namely, if you modify this data, then the hash value will change, and if you have already remembered the digest of the data, you can later verify whether this part has been modified or not, just by computing again the hash of it and check if it equals or not. Because of the collision resistant property, no one can modify the data in a way that the original copy and the modified copy will result in the exact same hash. With this building block, we can build a more complex data structure called blockchain. So it is nothing but a concatenation of those hash pointers. So we have a set of data and a set of hash pointers. So the second hash pointer points to the first data together with its hash pointers. So this hash is calculated, takes the whole thing as input, and it is chained in this way. The good thing is that if you modify this one, then you have to modify the hash pointer of the next block, and because of that, you have to modify the hash pointer of the next block, and so on and so forth. The modification has to propagate along the line, together with alongside until the last point, or last hash pointer, and due to collision resistant property of the hash function, any modification will be detected. Okay, any questions?
So how do you retrieve the data? Do you use through the pointer or just by the hash value?
So you use the pointer to locate the location of this data, and then you compute the hash of the whole thing to verify whether this data has been modified or not. Okay, that's a good question. Any more questions? Okay, so let's continue. So the second important primitive that I want to introduce is so-called digital signatures. So in everyday life, we sign things in a daily basis. We sign contracts, we sign on bank notes and things like that. This digital signature works in a way very similar to handwritten signatures. So what we expect from signatures is that only I can sign on behalf of myself. No one else can forge my signatures. So digital signature works in almost exactly the same way. It consists of two algorithms. One is the signing algorithm, and the other one is the verify algorithm. The sign algorithm takes input the thing you want to sign and the secret key of you. It generates some output. And the verify algorithm takes in the signature and your public key, and then it will return one big value indicating whether the signature is originated from this public key or not. So because this signature, this signing algorithm takes input both the message you want to sign and your secret key, this signature is tied to that particular input message. So you cannot use one signature and cut and paste into another document and say that you signed that another document. So this is a typical usage for digital signatures. Alice holds a pair of keys, public key and secret key. We publish her secret key to some public directory that could be retrieved or seen by anyone else. So to show that if Alice wants to sign some messages M, then she runs this signing algorithm to sign on this message and transfer the message together with the signature to Bob. And Bob can retrieve Alice's signature from this public directory and then run the verification algorithm. So if it is true, then Bob is guaranteed that indeed Alice signed on this message. So just like hash functions, we have some properties that we expect for secure digital signatures. For example, we require a digital signature scheme to be correct. Namely, for any message signed by the secret key, the verification algorithm should return true. And one important property of digital signature is so-called unforgeability. Namely, an attacker cannot forge a valid signature that under the public key that he does not have the corresponding secret key. Even if he sees pairs of signature message pairs. And because of the unforgeability of digital signature scheme, it also has an additional property called non-repudiation. Namely, once you sign some message, you cannot deny the fact that you already signed it. Because only you can generate a signature that can go through this verification algorithm. Only you who is in possession of the secret key can do so. So the signer can never deny issuing of a signature. So this property is very crucial for any cryptocurrencies, because in cryptocurrency we pay coins to someone and then we sign such payment using digital signature scheme. In this way, you cannot deny the fact that you pay the coin to someone, right? Otherwise, you can double spend your coins. You pay your coin to Alice and then pay to Bob at the same time, and that's something that we don't want. Okay, combining hash functions and digital signatures, we have so-called hash and sign paradigm. Why do we need such a kind of paradigm? Why do we need to introduce this concept? That is because some signature schemes can only sign very short messages, and if you really sign a long message, then it may take a very long time. That time may depends on the length of the message, and the output of the signature may be also dependent on the length of the message. This is some property that we don't want. The solution is that we first hash the long message into a short digest using the cryptographic hash, and then you sign this short digest of the message. So we sign hash of the message instead of signing the message itself directly. So in cryptography, some researchers have already proven that this approach is secure. Namely, if the digital signature algorithm is secure and the hash function is collision resistant, then the resultant scheme is a secure digital signature scheme. This property is also used in Bitcoin. Because of the unforgeability and non-repudiation property of digital signature schemes, we can use the public key as the identity in distributed in a decentralized network. The idea is that only you who is in control of the secret key can sign on behalf of the corresponding public key. So if you are not in possession of the secret key, you cannot pretend that you are the one. You cannot pretend that you hold the public key. That means to create an identity in a decentralized network, you only need to create a random digital signature key pair. Because anyone can make arbitrarily many identities as he or she wishes, so it provides some sort of anonymity in this network, because you can always generate a new identity and give up your old identity, and it is conceptually hard to link the old and the new identities. And in fact, these identities are the addresses of Bitcoin, namely, in Bitcoin nodes, the only way to identify someone is through this public key of the digital signature schemes. Okay, that's pretty much what I want to talk about cryptography. Any questions so far? Okay, if no, then we proceed into a simple cryptocurrency that works quite similar to Bitcoin in my point of view, but it has some unpleasant properties that we will see soon. Okay, this currency is called the Luffy coin. So if you like One Piece and you know that the currency in this comic is called Betty. The first letter is exactly the same as Bitcoin, so I choose this deliberately. We will build up this Luffy coin using only two primitives we discussed before. And the rule of this currency is very simple, only 4 rules. Let's take a look at them one by one. The first rule is that transactions has only 2 types. The first type is create coins, and the second type is transfer of coins, namely you pay your coins to someone else. This is pretty much the same as in real world, only the bank can issue money and you can pay your money to anyone else. The second rule is that only Luffy can create these coins. And the third rule is Luffy can create as much as he wants. The fourth property is an important one. It says that all transactions must be public to everyone in the world, and this transaction must be certified by Luffy. And the way Luffy certifies transactions is to sign a hash pointer of all the transactions that happened before. So we will talk about this point in the next slides. So here is a picture showing what do I mean by signing, a blockchain signing all history transactions. So the blockchain is organized as follows. The data are the transactions. And also we have an ID for these transactions. So it's an ordered list of transactions. So the smaller IDs represent that this transaction happened in the early time frame, and this transaction happened after this one, and so on and so forth. These data are organized in a blockchain data structure that we have just discussed. So together with ID and transactions, we have a hash pointer that points to the previous transaction, and things like that. And ultimately, Luffy will sign the last hash pointer using his private key. So in this way, Luffy implicitly endorses satisfy the whole transactions that has occurred so far.
I'm sorry, what is SK looping?
The secret key, the signing key of
Then, as you mentioned just a little bit earlier, when we try to sign a long message, we first use some kind of a hash function.
Yes.
So
yes.
do we use that here?
So we implicitly use it here.
Okay.
We are assigning this particular hash pointer instead of assigning the whole thing.
How long does it take to sign this chain? I wonder if this chain is very long.
So because you only sign this short digest, you are not explicitly signing this long thing. If you have a new transaction comes in, you append it here and then calculate the hash pointer of this new data block and then sign that short message here. Okay. The property is that everyone who sees the public key of Luffy can verify that whether Luffy endorsed the thing, and everyone can look into the history and look into the transaction and check whether that transaction exists in the blockchain and verify correctness of it. Okay, so I mentioned there are two types of transactions. One is create coin, which is here. So in a create coin transaction, Luffy can create multiple coins. For example, here he creates these many coins and he explicitly assigns these coins to someone. For example, he assigns 320 baddies to the one who is in possession of public key 1 and assigns some other amount of baddie to someone who is in possession of some other public key, things like that. Notice that each coin has an ID, coin ID, which reference the ID of this transaction and also the order of this coin. So this coin is created in the 73 create coin transaction and it is in the first row of this transaction. And remember, our second rule and the third rule is that Luffy can create coins arbitrarily, so he does not need to show any reason for such a create coins action. Okay, the second type of transaction is pay coin transaction. So in this transaction, one has to specify what kind of coins you want to, which coin you want to spend. For example, here the coins that is going to be spent is these 3 coins, and also specify where these coins goes into. So the owner of these coins pays these coins to the recipient specified in this transaction. So to make sure that the owner of these coins indeed wants to pay their coins, they have to sign on this data using their public key. So the signature of the owner of the coins has to be appended in this transaction. We call such a transaction valid if these coins are valid, namely it is the result of some previous create coin transaction, or it is the result of some pay coin transaction listed here. We can check these things in the blockchain because the blockchain has been published and everyone can check whether these transactions are signed by Luffy and things like that. And also, of course, we require that the number of coins equals the number of spent coins, things like that. And if this transaction is valid, then Luffy will append this transaction in the blockchain and sign on it. So after that, everyone will know that this transaction is valid and Luffy has certified it, and the money really goes to the recipient of it. Okay. Any questions? Let's talk about some properties of the Luffy coin we have just developed. So this cryptocurrency is pretty good in the sense that Luffy cannot create fake transactions because a transaction is valid if all the owner of the coins have signed this transaction. And because the unforgeability of digital signature schemes, Luffy cannot do so because he does not have the corresponding secret key of those owner of the coins. Also, user cannot spend their coins twice because everyone can look into the blockchain and check whether those coins has been spent before or not. And also, Luffy cannot easily modify the blockchain because as long as someone keeps track of this single shot value, then he can make sure that Luffy does not have the ability. If Luffy modify previous blocks, then this thing must change because of the collision resistant property of the hash function. So these things are pretty good, but there's something that bothers us. For example, Luffy can create arbitrarily many coins, so this is obviously a problem. And a more subtle problem is that Luffy can refuse to sign if he does not like it. Maybe he just falls asleep, maybe he wants to go to have something to eat. Once Luffy refuses to work, then the whole world stops. You cannot make any transactions. So the main problem of Luffy coin is that we have put a lot of trust to Luffy, and he works as a centralized authority who is in control of everything. What we want is to remove such kind of authority and make things work in a decentralized manner. And this is exactly what has been achieved in Bitcoin. So let's talk about Bitcoins. Turns out Bitcoin works in a way very similar to Luffy coin. It is actually very similar to a decentralized version of Luffy coin. So to make it decentralized, it has to solve the following questions. For example, who maintains the blockchain? Who has the authority over which transactions are valid? In Luffy coin, the validity of the transaction is ensured by Luffy signing it in the blockchain. And also, who create Bitcoins? In Luffy coin, it is Luffy who create coins. And if we remove Luffy, then who can create Bitcoins? Things like that. So we will solve these three questions in the next few slides. So here's the simplified Bitcoin approach. So at this moment, allow me to make a small assumption. So this assumption may look a little bit weird to you at the beginning, but I will explain it in the next few slides. So the assumption that I'm going to make is that every 10 minutes, a random node, namely a random participant of the network, is selected. So why do we want to select this random node? So this random node has the responsibility to propose the next block. So he is the one who collects transactions from a distributed network, and then he collects all those transactions and make it into a single block and then append it into the blockchain. It seems that this node has a very powerful node because he's the one who makes the next block, and because we are talking about a network in a decentralized network, distributed network, this node may or may not be honest. Maybe this node is a malicious node and it includes some invalid transactions. And how do we solve this problem? The way we solve this problem is that the rest of the network, namely other nodes in the network, will endorse the validity of this new block by either accept this block or reject it. If they accept it, it will extend the blockchain including this new block. If they think this new block is invalid, it will just ignore it, pretend it has never seen this block before, and then extend the blockchain as if this block has not been proposed. This approach seems quite stupid, but it works in a very good manner. Okay, this is just summarize the algorithm I just described. New transactions, namely if Alice wants to pay some coins to Bob, it create a transaction and then broadcast this transaction to the rest of the world. Every node will connect new transactions. It monitors the traffic and then receives new transactions. And then they will connect the outstanding transactions into blocks. After a few minutes, a random node is somehow selected, and then it will propose its block to the rest of the world. And other nodes will accept it or reject it. Okay, any questions? If no, then let's take a look at what could go wrong in this approach. So let's say we have a blockchain here. This is the existing blockchain. So somehow we have a new block being proposed which contains a transaction. Namely, Alice wants to pay some money to Bob. So this transaction is signed by Alice. It contains information saying that I want to pay some money to Bob. Namely, the one who is in possession of the public key, PKB. So it refers to some previous coins in the blockchain. Namely, Alice wants to pay the coin created here to Bob. So let's say this block, someone proposed this block and we broadcast this block to the rest of the nodes. And later, maybe due to network latency or inconsistency of the viewpoint of the blockchain, somehow somebody else proposed another block which contains another transaction. This transaction says Alice wants to pay the exact same coin created here to someone else, A prime. So that means this exact coin has been spent twice, once to Bob and once to someone Who doesn't know? Someone say me. So what will happen? We have two different blockchains, both are valid in the sense that all the transactions are signed by Alice and everything works, every verification algorithm will go through. And because of such kind of inconsistency, maybe someone else only sees the block here, but he does not see the block above. So that guy will try to extend the blockchain by proposing new blocks. And things may just happen and go on. So this blockchain may grow longer and longer, and maybe this block no one noticed and it just stopped here. So in this kind of scenario, Alice is a malicious user who tries to spend her coins twice. We want to make sure that all the transactions are valid and such kind of malicious behavior are detected and forbidden. So the way we discourage such behavior is that if we have if the one who wants to extend the blockchain sees two versions of the blockchain, then if this guy is honest, he will choose the longer version to extend. So in this way, the reason for this approach is that the longer the blockchain, the more confirmation we get from this network, because it has already get one confirmation from node 1 and get a second confirmation from node 2 and a third confirmation from node 3. In contrast, this blockchain on the upper part of the figure received only one confirmation from the network. So honest nodes will choose to extend the longer blockchain if there are multiple options. So in this way, once we see that our transaction has been included in a long-term blockchain, we are sort of sure that it will remain in the blockchain with high probability. Once your transaction remains in the blockchain, it will become valid and accepted by the world. So once it remains in the blockchain, you are sure that you receive the coins from someone else. So in Bitcoin terminology, the common practice is that once you have seen 6 confirmations, then you are sure that you indeed receive the coins from someone. Okay, any questions? So now we have resolved 2 questions. The first is who maintains the blockchain. Basically, everyone has the responsibility to maintain the blockchain, and everyone shows their confirmation of the blockchain by extending the blockchain. So we have the second question remains, namely who is responsible for creation of Bitcoin, and moreover we somehow generate 2 additional questions. So the 2 additional questions is, how can we make sure honest nodes will really follow the approach described in the previous slides? And also, how do we really select a random node in every 10 minutes? Bitcoin solved these 3 questions simultaneously in a very clever manner. So the way Bitcoin solved it is through so-called Bitcoin mining. So in Bitcoin protocol, it states that whoever is responsible for proposing a new block can append a special transaction called create coin transaction. So once you are selected as the random node to propose a new block, you can create coins from nothing. And moreover, you can specify the recipient of those created Bitcoins, which usually is the one who proposed the block. Of course, you can say, I create those coins and pay it to someone else. There's nothing preventing you from doing so. So this rule has the implicit effect of encouraging people to follow the protocol, because these coins can only go into your wallet if this proposed block remains in the blockchain. And to do so, you have to follow the rules, namely you extend the longest blockchain and includes only valid transactions. So this implicitly forces everyone to follow the Bitcoin protocol and then make the whole protocol runs smoothly. At the beginning of, in the early years of Bitcoin, the one who create a new block can get 50 Bitcoins as a reward. The amount of money decreases every 4 years, so in late 2012, the value has already halved into 25 Bitcoins. So because of this halving property, the total amount of Bitcoins that can be created is a fixed amount. So someone calculated it as 21 million. And notice that this is the only way we create Bitcoins. There's no other way of generating new Bitcoins. Okay, we solved the problem of creating Bitcoins, and magically we also make sure honest nodes will follow the protocol. So the remaining question is how to select a random node in every 10 minutes. Well, this is indeed the core of Bitcoin mining. So every Bitcoin node will compete for the responsibility of proposing a new block. The way they compete is to solve a puzzle, which is defined as follows. It has to find a nonce, namely some random value, such that the hash of this nonce concatenate with the previous transactions, namely the hash pointers of the latest transaction, namely this one. A nonce concatenate with the latest hash pointer of the Bitcoin blockchain. It needs to find such a nonce such that the hash of it is falls into a smaller range. The range is so small within the possible outer space of the hash function, such that it takes a long time to find this exact value. We guarantee that there's no efficient algorithm of finding this nonce by the puzzle-friendly property of the hash function discussed in the early part of this talk. So because of the puzzle-friendly property, nodes has no efficient algorithm except choosing random values and try to calculate the hash values and check whether the value falls into the target space. Once it finds such a solution, it proposes it broadcasts this solution to the rest of the world together with the block it wants to propose. And then other nodes will check whether it is indeed a valid solution and all the transactions in the proposed block are valid or not. And if all the verification passes, then the other nodes will accept it and then extend the blockchain according to the Bitcoin protocol. If people investing more computational power to solve this problem, then maybe this time we need 10 minutes to solve this puzzle. The next block will only take 5 minutes, and the third block may only take 1 minute. This is something we don't like, so in practice, the difficulty of this puzzle will be adjusted every 2 weeks, roughly. The way we adjust the difficulty is to shrink the target space to make it more difficult, or enlarge the target space to make it more easy. The rule of thumb is that we adjust the difficulty such that on average, every 10 minutes we will see a new block. The probability of a particular miner, Bitcoin miner, that can have the chance to find this solution and propose a new block and get a reward is proportional to the computational power that he or she possesses. If more people come into this game, then the target space will shrink and it becomes more difficult for anyone to solve this problem. Okay, that's pretty much the inner workings of Bitcoin. So at the end, let's put all those pieces together and go through it. So in Bitcoin protocol, every Bitcoin node do the following things. They keep a copy of the whole blockchain, the history of all Bitcoin transactions. It listens and collects new transactions that enter the network. So those transactions are outstanding transactions, namely they have not yet been included in the blockchain. These nodes can voluntarily compete for solving the hash puzzles, and if they get the solution, then the one who solved the puzzle is responsible for proposing the next block. And he or she will broadcast the solution and the proposed block to the rest of the world. And this new block will contain a transaction, create Bitcoin transaction as a reward. A transaction is valid if all the coins are valid and it has not been spent before. So to check that whether a coin has been spent or not, one can go into the history of the blockchain and keep track of all the Bitcoins that has not been spent. And also the transaction needs to be balanced, meaning input must equal to output, and this transaction must be signed by the owner of those input coins. And by the unforgeability of digital signature scheme, no one can create fake transactions or steal money from someone else. And this blockchain is only valid, this new transaction is only valid if it appears in the long-term blockchain. In practice, we need 6 confirmations before one gets really sure that this transaction is valid. So to wrap up my talk, let me just briefly talk about some applications of Bitcoin in research and also in practice. So Bitcoin has not only attracted attention from general public, it also attracts attention from security researchers. So some researchers use Bitcoin as a trusted random source because no one can really predict the next Bitcoin block. So one consider the blockchain as a verifiable random source because everyone can see it, look into the blockchain, but no one can really predict what is the next block. So some academic papers has already made use of this property and published some results. And also Bitcoin has the usage in an interesting application called smart contract, which will be discussed by Carson. So now I don't have any things to talk about. Any questions?
Or maybe we can have a Q&A session in the end.
Okay, sure. So then I will hand over to Carson to show you the.
So thank you very much for Yongjin's introduction. Actually, I would say that is the one of one of the most thorough and informative introduction to the inner work of Bitcoin I've ever heard in the past 2 months. Basically, he introduced all I have learned in the past 1 month, and he tried to get all things in 1 hour. So it may be possible for some of you to feel a little bit hard to understand. Thank you. So the first thing I would like to do is to. This is actually the app. Sorry. And I'm wondering how many of you have bring over your computer with VirtualBox installed? If you have, you can ask for a USB. I have passed through somewhere among you. So you can find a virtual machine inside a USB, and you can copy it, unzip it, and install that virtual machine in your VirtualBox. So that you can follow my demonstration or tutorial later, several minutes later. So I'm Cousin. I will take the next about 25 minutes to give you a general introduction to smart contract. By general introduction, I mean I will not give you, I almost will not give any technical details or math details about smart contract. I'll basically introduce the sense of smart contract. Sorry, I opened the wrong page. Okay, so I'm Carson. I'm from the CSE department from CHK. So let's have a preview of the content I'm going to talk about. Firstly, I will give a basic recap of what is blockchain and Bitcoin, which is just introduced. And then I will introduce what is smart contract introduce the concept of smart contract using some examples. And then I will tell you why it is important by introducing the property of smart contract. And before the end, I will give you a demonstration using Pi Ethereum, which is developed by Ethereum. And finally, I will give you some pointer because I think there are some kind of like computer science guru here sitting here. And my introduction is actually a very introductory. And if you want to go deeper, you can follow my pointers and you can find something very interesting. So let's start with the recap. Possibly you may feel a little bit drenched by the so many math details just introduced. It may be very informative. So in a common introduction, you can just think of it as a black box. Think of it as a black box. So what blockchain do? Blockchain is basically a secured, decentralized database that stores all the transactions. So all the things that it does by hashing about all those things, the purpose, the intention of it is to make a secure, decentralized transaction database. Okay, so we have the first keyword there, secure. And then what is Bitcoin? Bitcoin is actually an application built on blockchain that has two functionality. The first functionality is every one of us have a wallet. So cousin has a wallet that can only owned by me. And the second functionality is transaction. That is, I can make transaction from my wallet to somebody else's wallet, to exact target's wallet. So, and because Bitcoin is built on blockchain, so we claim that blockchain is super secured. So nobody else can use my wallet, and nobody else can somehow claim that he sent my money. Okay, so 3 keywords. The first thing is it is secured, and second thing is 2 functionalities of Bitcoin: wallet and transaction. With this in mind, so what is smart contract? Smart contract is quite simple, basically with the functionality of Bitcoins, plus 2 things. The first thing is Bitcoin can launch a transaction with terms and conditions, which is also known as contract. And it can ensure the execution of terms and conditions. So what does it mean? Basically, so I create a contract saying that I will pay you $10 if you help me to finish the homework. So $10 and the homework, there's if else condition there. If you help me to do the homework, I will pay you $10, right? So that is a contract. That is a very simple form of the contract. And I can create a contract like this using smart contract, and the smart contract will help me to ensure the execution of it. So if you do not help me to, somehow you do not help me to do the homework, the $10 will not pay to you and will pay back to my wallet. So we have 2 keywords here in this slide. The first thing is the contract. Smart contract is basically the contract. And then what Bitcoin or what blockchain can help us is it ensure the execution of the contract. And actually it's also known as fairness. So to be more specific, I will introduce with 3 examples, which is broadly used in the introduction of smart contracts. So you can find the example codes of these 3 examples somewhere else. I will point you in the final slides. So first example contract is called 2 people lottery. The so-called 2 people lottery also we have 2 people. Okay, Alice and Bob. Alice and Bob. This contract allowed 2 people to join in. So Alice and Bob joined this contract, but each of them paying $1 to the contract. So contract's right here, and Alice and Bob pay $1 to that contract. And the executor is not necessarily one person. You imagine there's an executor. Executor generate a random number. If the number is odd, then the $2 goes to Alice anyway. And if the number is even, the $2 goes to Bob. Basically, that is a random lottery, and we can see that is a fair game. And the second. And by this example, actually we can formulate it into a contract like this. If the number generated is odd, Alice pay Bob $1. Bob pay Alice $1. Okay, so if the number is even, okay, never mind. So somehow somebody pays somebody else. Okay, so the contract is basically like this. In this contract, you can see that this contract has a structure. I call it structure of if-else condition. If something, then I do the transaction, right? So compare with what Yongju just introduced about Bitcoin. Bitcoin can do transaction, and in smart contract, we can have if condition. So that is basically the most simple structure of a contract can have. So then let's look at a little bit more complicated example, which is known as sport betting contract. Sport betting contract, so there are kind of like 100 people join this contract. I just named N here. 100 people join this contract, but each of them paid $1 to the contract. And some of them, let's say 40 of them bet on Arsenal. Anyway, I'm not a fan of it. Never mind. So while the 60 of it pay on the other side, I don't know what the other side is. And let's say the other side win. Okay. So the 40 people will pay the rest of 60 people in total $40. So this is a contract. If we create it using smart contract, and basically they will also kind of like basically it's also kind of like if-else condition contract. If somebody win and we make the transaction like that. And somebody may say, well, is contract just like that simple? If condition, let's make a transaction. If condition, let's make a transaction. And if that is the case, well, then I may not be necessary to make introduction here. So actually, there's a super complicated contract, as complicated as you can imagine, as complicated as you can see in real life. So basically, there is a example. I call it bank contract, and I will use this example in a later demonstration. So you may think of bank as a service provider. We can store our money and we can deposit our money into the bank, and we can withdraw money from the bank. So basically, we think it's a service provider, and actually, bank can provide us with some different kinds of contract. For example, let's say a bank, they charge you for 1% of tax when you transfer from one wallet to another wallet. By doing so, he or she claimed that, oh, I take the tax of it, and we will do public welfare. So Zuckerberg just claimed that he will do some public welfare yesterday. Anyway, so this is kind of like a contract, but the contract is very complicated that you can hardly describe it with the if-else condition and with transaction, because it basically involves too many entities here in this contract, and so I would say it is very hard for you to formulate this into if-else condition with transaction inside if-else block, or you can try that later with the VM. So let's look into one example a little bit deeper. So with the knowledge that we just learned, so I just introduced you what is a contract is, and I think most of you know what a contract is. So how the Bitcoin comes in. So I will give this slides with timeline in, bring the timeline in. So in the very beginning, Alice launched a contract which is known as the two-people lottery. Then sometimes later, the blockchain mining. Okay, sometimes later, Bob see this contract and Bob think, oh, that's a deal, and I will join it. So Bob joined this contract. Sorry. It's a little annoying. Okay, Bob saw this contract and thought it was a deal, and he joined that contract. So the contract basically have two people in, and the next block, the executor of the next block think, oh, we already have the necessary condition for the execution of this contract. So in the next block, the contract is executed in decentralized manner anyway. Right, and a random number is generated, and then somebody judge whether it's all even, and then money passed from Alice to Bob, Bob to Alice. You may ask, if you if you have this question, then I would say it's fair. Okay, so you may ask, oh, okay, so let's do a decentralized execution. Then if all of us own the transaction database, and all of us will create a different random number, right? So how to solve it? The answer is actually quite simple, but actually smart. So in the last block, and we can create a hash of it, right? And we can create a hash into a number, right? And we can see whether that number is odd or even, right? And then it's a random number, but it's a fixed random number. If you don't understand it, then this is encrypted channel anyway. So let's block. So you already have timeline in it, and so I will give you a little bit more about the blockchain concept. So I will bring in the blockchain concept here. So let's say in block 100, so there's 99 or 100 block somewhere here. Anyway, so here Alice launched a contract. So tax info. Never mind this tax info. It's just okay. So Alice launched a contract info here, and it is just stored in this block. And after some time, mining to block 110. So Bob sees this contract. Bob joined this contract by doing a transaction. So a transaction is recorded in this block. Right. Okay. So we keep on mining to next block and 110 at 111. Okay. So the executor of this block, a random pick executor of this block, they find that actually the contract of it is the necessary condition for the execution of the contract is satisfied. So the contract is executed, and the result of the execution is made into a contract. It's made into a transaction, sorry, and this contract will expire. So basically, that is how a smart contract works, and by introducing it using the most basic
So
example.
what is the meaning of the block number?
The block number. As we just introduced, there are blockchain, right? So the blockchain has a sequence number. I just do not want to use hash number here.
Just the first block.
The first block, second block.
So each block contains one transaction.
Not necessary. It can contain as much.
You can pack
right.
many transactions in
Right.
one single block.
Yeah, but so who determines the number? So how large is the block?
The executor decide how large the block it is. So, for example, I am the executor of this block. So before me, there are only 110 block, right? So I solved the mathematics. I solved the number guessing problem, and then I claim that I solved it, and then I just collect, because I already collect a lot of transaction information from the P2P network, and I just make my own block. This is my block. I claim that this is my block, and everybody else should accept it because I'm the executor.
Also, the one who finished a whole series of transactions will have its own block as they increment the block number.
Basically, yes, but they increment their own block, but if they can propagate the information of this block if and only if they solve that number guessing problem.
Yeah, the point is that if one guess the number and then he finish the transaction, finish the smart contract as you guys talked about, and then he is privileged to create a new block.
The privilege of creating, I would say, the creation of block is a right owned by everyone. So everybody of you create this block 111, the number of this block, but nobody else would think it is authorized until you solve the number guessing problem.
So no matter when you are finishing a contract or you are accept a contract
Right.
as in the block 110, or you are propose a contract, you will create a new block.
I would not create a new block. I would propagate the information of my contract. And for example, if I
I know they may not be accepted, but I just say each time they do something, they create a new block.
basically you can think it is, but right, if they do not do something, they will also create a new block because somebody else did something.
Yeah, I just want to know what block is for, so what information I want to contain that. If I'm guessing previously is that when someone executes some transactions,
Okay.
they create block, and they say that if there's nothing, they could also create the block. So what block is for?
Block is used to store the information of transaction. Basically, if you say yes, nobody in the world create any transaction. Basically, we do not need to create the next block. Yes, it is true, but well, you know. Right. Okay. So I will go on to introduce. I'll move a little bit faster. So if you still remember, I just introduced you 3 examples. So 2 people lottery, sport betting, and bank contract. Actually, if you think of it a little bit deeper, you can see one problem. So for sport betting, this example, actually we need some outside information. We need somebody else to tell this network who exactly wins. Well, this actually brought into another centralized problem because we need to trust another institute. That we trust another institute that what the institute said is truth. Well, that basically divide the smart contract into 2 different kinds, I would say. So basically, they are known as deterministic and non-deterministic. So for deterministic contract, the execution of it does not require any outside information. For the typical example is lottery. So for the lottery, everything is done inside the network. We do not need any outside entity to offer us any information. For non-deterministic smart contract, we always require somebody else outside this network to provide us with information, or in other cases, help us to do the execution. So for those outside information provider, we call them Oracle, not database. Oracle. Oracle in Chinese is 圣人圣者, just like Confucius, something like that. That we believe to be justified. Okay. So this is an encrypted channel. If you do not interested, you can just pretend you do not hear that. So a non-deterministic smart contract requires Oracle. So we need to trust a centralized institute. So that would bring into one problem that it actually hurt our fairness of this infrastructure. So basically, that's a very good point, and actually, this is a research frontier of Bitcoin smart contract. So after doing some investigation, I proposed 3 possible ways to help you to accept that. But firstly, there are already some trusted institute that well trusted by everyone else in the world, such as Bloomberg terminal, because if you work on financial things, you will know a Bloomberg terminal and so on. But we're going to say that they are still centralized, right? I'm still not happy with that. Okay, so there are 2, as far as I know, there are 2 projects known as Truthcoin and Augur. They are exploring ways to somehow to improve the models for Oracle to work into smart contract. I will hit all the details here. If you want to know, you Google it. Using technique like PCA, principal component analysis, to reduce the to improve the security of the infrastructure, I would say. So if you're still not happy with that, just think of how many PhD are working on that to get a degree, and how many assistant professors working on that to get a tenure. Anyway, so encrypted channel end. So let's talk about the property of smart contract, so that I will tell you why it is important the leading financial technology. Also, by the way, financial technology is not known as a financial technology to help the bank. Actually, as far as I know, financial technology is the technology to take the place of the bank. They may not be happy with that. So the property of smart contracts basically it's basically it inherits or it owns all the property of Bitcoin. So transparency, decentralized, and trustworthy, anonymity, and maintainability, efficiency, a lot of things. I will hit the details here. If you want to know it, you can Google it. So the potential impact of smart contract is basically, as I told you, it may take a huge part of the service provided by bank and some law firms, because basically they are working with contract, right? But there are one biggest obstacle we have to overcome. That is, as I just mentioned, we need to solve the non-deterministic contract things, because if we still need somebody else to interact with this contract, then we actually doing the same thing as what banks and law firms do nowadays. So I will give you a short demonstration using code things. The things I use is called Ethereum. It is a infrastructure created by this. I'm sorry, I forget his name. Somehow, because his name is not English name, so somehow a weird start with B, I think. You can Google it. The founder of Ethereum. Okay, I know that he's very young. He born in kind of like 1994. So when he found Ethereum, he was only kind of like 18 years old. And Ethereum crowdfunded to 20 million US dollars back in when he's 18 years old. So he dropped out of college. Right, this is how successfully works. So they create a lot of things, a lot of very interesting things. If you want to know more, you can just Google it, and it's very Googleable. And actually, the reason why I'm here to give this talk is that I was invited to join a workshop held by you can see this young guy here, and Andrew Miller, and Peter, and a lot of big name in the cryptology and Bitcoin industry. So, oh, by the way, so we just talked about bank. So this guy from UBS, I don't know. So anyway, so okay, I will give you the demonstration, and I'm wondering if you want to have the virtual machine, you can download it directly from this address. If you cannot download it, you can find a USB. If you do not have VirtualBox installed, or you do not have computers, so just watching to do the things. For those people who have the virtual machine launched, the username of the virtual machine is user, the password is DES. So the code is accessible in this URL. Okay. I just SSH into my virtual machine. So I just somehow, I don't know why it is so fast. So this is the code I provided. Oh, by the way, you can just, if you want to look into the source code, you can just visit this website. Oh, sorry. I will provide you with the I will share this. Okay, so you can have access to my slides right now, so that you can have access to any material, any address that point to in my slides. Okay. Notice the KTD is capitalized. Maybe you get that? Oh, I see a lot of you joining to this slides. Okay. And the address of my code and the VN address is right in the slides 14. Okay, so let's look into the code. Before everything started, I would like to thank Ethereum Lab because they provide me with the virtual machine and basically this code. So let's start. I'm using Beam anyway. So in the very beginning, there as you can see here, a huge block of red code. You don't know what it is. Never mind. Just see there is a serpent code. I don't know how to actually pronounce that. Serpent code right there, and then follow up with a long string. Actually, if you know Python, oh, by the way, this is Python code. So if you understand that this is actually assigned the entire string to that variable. And what is that variable? That variable actually is content of the contract. So remember that serpent code is the contract. and we just firstly we skip the entire contract to see the logic of the code. Because this is doing simulation, so basically I and L is I and Bob. Firstly, we create a public key by using the address provided by tester K1. Then I create a tester state, never mind S and never mind S. Anyway, so C by C I call the creation function of the contract by fitting the creation function with the content of my contract. As I told you, the servant code is the content of the contract. Okay, so then I do the first action. The first action I do is, oh by the way, this is a contract of bank. Okay, so the first thing I do is, so for sender K0, K0 deposit 1,000 to the bank. Right, you just remember that. K0 deposit $1,000 to the bank. In the next action, I do K0 withdraw $1,000 from the bank. So it deposit and then it withdraw, and I just want to demonstrate that somehow you can do that. And in the third action, you can see that this action is done by K1, but we did not. K1 has not done anything about depositing money into the bank, so we guess K1 cannot deposit any money from the bank, so we will have this failure message. And in the fourth, right here, in this action, K0 and K0 comes back. K0 said I deposit $1,000 again into the bank, and then K0 transfer $500 to K1. And that's the end of all our action. And then we just print out the balance, the bank balance of K0 and K1, and see whether everything is going as we expect. So Python, in case you cannot see that. Oh, it is already like this. Okay. Hopefully you can see that. So, oh, by the way, Ethereum Lab call their coins WEI, I don't know, WEI. I haven't asked them why they call it things. So 100 WEI successfully deposited in tester K0's account. If you still remember, we firstly do deposit and then withdraw, right? So then 1,000 WEI successfully withdraw from tester K0's account. So K0 deposit 1,000, K0 withdraw 1,000, and then K1 tried to withdraw 1,000 WEI from the account, but he or she failed because he or she has not do any deposition into the bank. So and then K0 do the deposition again into the bank, and then 1,000 WEI is deposited. 500 WEI is transferred from K0 to K1, and then if you know a little bit math, then K0 has 500 and K1 has 500. Right, basically everything works as we expected. What should be done by a bank? So now let's do. So let's look into the. Okay, let's look into the contract part. I'm using Sublime because I think this color made me feel a little comfortable. A little bit more. The contract is written in a script language called Solidity. Anyway, Solidity. And it is not Python, although it looks like. It is not C, although it looks like. So it is Solidity. But it's readable, so I will explain a little bit for you. If you do not understand, you can follow my pointer. Okay. So basically, it has 4 functions. The first function is deposit. So the first function, somebody, for example, K0 deposit how many money into the bank. right? So the deficit function is quite simple. You just create a storage and storage the center into the plus by the value. And the withdrawal function is also quite simple and intuitive. And you just check whether they have enough money. If yes, then send a value. And then if yes, then withdraw the value. Else, return an error message. Then the transfer function basically is we subtract the amount from the sender, and then we plus the amount of the acceptor, and then everything goes as we expect, except that there is a little bit of error handling here, right? Then the balance checker function is basically return the storage seller's balance. So I promise you to give a demonstration about the contract I just introduced. So by charging those who made transaction anyway, can you see that? Okay, so I will work directly on the end. So basically, it's quite simple to make modification on this contract. So let's say every time you make a transaction, you'll pay $1. And then we create an account called welfare. And the welfare plus by 1. So by doing this modification, we can see that every time you make transfer from one wallet to another, your transfer value will be subtracted by 1. But the public welfare account will be plus by 1. And then we need one more function to check the welfare, right? Or else we don't know whether the welfare is in it, right? So then we return self-storage, it should work correctly. By the way, I need to. So I don't like it. Okay. So in the end, we will do a check. So we need check welfare. Sender can be anyone. So we print the result. The public welfare is, and then we just okay. It should work correctly if I can remember any time. Okay, so some typo happens. Then I have attribute check elf. Okay, I may have a typo on the function name. So we name the function as check. Okay, sorry, welfare does not spell this. I don't know. Anyway, never mind.
I think you have the O to 0. Check.
So the morph is slow, anything can go wrong. Where is it? Sender. Okay, sender. Anyway.
And the print is seems to be all but in 0.
Oh, right. So this bug may call me sometime. Okay, this is terrible. Oh, hopefully, so happily we found that it works correctly. I did not print the headline to, somehow, strange things happen. I don't know why there is this line here. So anyway, let's neglect that. So everything else goes as what we expected. set this line. Anyway, I will check it later. And this line is what we added. The balance of the public welfare is added by 1. And then next we can see K0 try to transfer 500 way to K1, and K1 is now get 499. Never mind now, let's decline that. And so let me just convince you by doing 2 transactions, making 2 transfer. So here we just make 1 transfer of, okay, just let's suppose K0 has deposited 2,000 and 1, 2, 3, 4, 5. And then this transaction is done twice. The transfer is done twice. Boom. Okay. So as we can see, previously is 1,000 Wei deposited into K0's account, and now we have 2,000 Wei. And K0 transferred twice, transferred 500 Wei to K1 twice. By doing that, the balance of it basically is 1,000. But as what we done just now, we charge the transfer action by $1 each time. So we can see the public welfare account is currently 2 Wei, and K1 actually just accept 998 Wei. So by doing that, actually, if you look into a little bit the source code, I don't want to go very deep into it because it takes me really some time to understand the structure and the inner design of the Pi Ethereum. Oh, by the way, Pi Ethereum, Ethereum is currently running their own Bitcoin-like currency network, and they support smart contract. So basically, what Ethereum support, and actually we can use it to understand smart contract. Understand the smart contract is this is the content of contract, and if you look into our example of the Pi Ethereum, you can find out that actually they are declaring a class, a Python class, or a C class. Anyway, it's just like an object, or you can understand it as a class. Anyway. So you can define any function you like, any action you like, as what you do in writing your program in an object. So that will just define the action of the contract. So as I told you, we can have a super complicated object because you can define as what you like in just like what you program in an object or in a class. The reason why I do not know whether it's a class or object because I really don't know. So that's the end of my demonstration, and hopefully you have your virtual machine run. If you cannot, you can ask me later because I failed several times, so I know how to fix the problems. So I have finished up the demonstration, and before the end, I would like to answer a frequently asked question because it actually confused me for a while. How do we understand mining? Actually, it is very similar to that question. I'm just being asked. So basically, I do not know how many of you have the background of digital circuit. So basically, I understand mining as the following. So each mining signal is just like the clocking signal provided by the digital circuit. So the purpose of the clocking signal in the digital circuit is just like doing the just doing the synchronization. So to make each component of the entire circuit know that, oh guys, we enter the next state. And actually mining doing the same thing every time we move into the next block. And this information is broadcast as a clocking signal, you can think of it, to inform every node in this network that we enter the next state. Okay, that's how I understand mining. And here's the Q&A section.
Let's give a big hand to the speakers. Okay, so any questions for Carson or Yongjun?
I have a question. Why your simulation goes so fast?
Because, well, the mining, if you notice, I just comment out the mining process.
Okay, so you
Right,
don't
actually I
really
did not, right.
contact the blockchain really to
Right, because actually this is a testing environment. So even if I add the mining inside the code, the mining actually is super easy. That is, I can get the answer in the very first try.
So how long will you expect it to respond once you say you want to deposit? How long will you get the information?
Basically, I would say at least 2 or 3. I need to examine my code, but basically I would say basically if carefully programmed, I would say at most 2
2 minutes or 2 seconds?
two blockchain.
Blockchain.
Right.
Okay, any other questions?
So basically, based on the explanation, so you just demonstrated code, right? So we have some numbers of transactions here, and after each transaction, we just make a block that we make a function out of for the next transactions. And if we have a lot of transactions before, then this task is supposed to be very slow, right?
Support to be what? Sorry.
So in demonstration, we have gone through several transactions.
Right.
And after each transaction, we have made a block, right? Or
No. So let me explain like this. So how blockchain works. So basically, let's imagine there is an entire P2P network. Oh, by the way, blockchain is built on P2P network, as far as I know. So there's an entire P2P network. So every node there just broadcasts information to their neighbor. And now the very first, or somewhere in the middle, so 100, just broadcast I made a transaction to their neighbor. And then the transaction is stored in a kind of like a buffer, and then the next node, the neighbor of the node, just collect the transaction if they want. They can reject to collect the transaction from the buffer into a block they try to create. So basically, Yongjun is the node next to me. He's my neighbor. Yongjun created a transaction and he sent to me. So that his transaction is stored in a buffer of mine. So I'm working on creating my block. My block can contain a lot of transactions, not necessarily be one. They make it 1,000, 10,000, and then I see his transaction, and I can choose. Actually, I can choose to reject his transaction. I do not store it, but basically I'm a good man. Okay, so I store his transaction and append it into my block. So then my block contains the information of Yongjun's transaction, and I will claim that, well, this transaction is already, but I do not claim anything anyway. And then while I'm building my block, I'm actually using my CPU to solve the number guessing problem. So somehow, luckily, I solved the problem, and I claim to the entire network that I find a number, and simultaneously I broadcast the information of my block. Basically, so everybody else know that, oh, there's a guy there. He solved the problem and he got his block information. So I just accept his block information, append it to my existing blockchain. So, and I think clear.
yeah.
Right.
So since that problem solving procedure is kind of random, I mean,
Right.
nobody knows who solved
Right,
the
exactly.
problem. That's the reason why it's totally random.
Exactly. Right.
Okay.
So basically, that is why Yongjun asked me just now. Why Yongjun asked me just now how many time it would take to do the restore and deposit, because we need to ensure some time. That actually, the time can be calculated mathematically with a level of confidence to say that after a certain amount of blockchain, this action will be accepted by the entire network. Right.
Thanks.
So hopefully my answer will help. Any question?
So each node will locally be storage the transaction information.
Right.
So when the transaction is there are many transactions, then this information will be very large.
Have you ever tried to install Bitcoin?
No,
Basically,
How long the blockchain is?
I have no idea of that.
basically they're really kind of like 200 20 million or 200 million transactions in the blockchain. So basically, if you are new to Bitcoin and you try to install Bitcoin on your laptop, good luck to you.
I didn't show the numbers, so basically currently the length of the blockchain is several kilobytes or 20 kilobytes.
So actually, Yongjun, I would like to emphasize is basically I just keep saying it wallet, but actually there is nothing like wallet in the Bitcoin world. Every time you need to traverse is the entire transaction history to decide how much money that one had. Actually, that's a little bit time consuming, but there are a lot of programming tricks, I would say, to use buffering things, because you can see that it's actually linear, and if we carefully program it, and we can use some buffer things to reduce the computation time. Right.
Okay. So,
I'm not sure again how everyone else would know you have guessed the number. So
Get the what number?
So when you guess the number, so you could you have the privilege to
Oh, yeah.
all the others.
Right.
Yeah. So how could others know you have guessed?
That is the property introduced by Yongjun. That is, they cannot know they do not know what the number is. But if I give them the number, they can verify that it is the number.
Oh.
Right.
So to verify, you just recalculate
Right.
the hash and check whether the result falls into the target.
By the way, if you want to know a little bit more, a typical example of that kind of function is factorizing. Okay, just forget it. Okay.
So we
Okay.
just publish the solution and everyone can check whether that's easy.
Right.
Well, how fast are propagations been?
How fast? What propagation? Oh, information propagation.
Yeah.
This is kind of like a very low level internet, very low level network knowledge. And unfortunately, I'm not confident to answer that question, but I would say several blockchain. Right.
I think that depends on the topology of the network.
Right.
The network connection, things like that.
What I thought was that if somebody else solves the questions and propagate, I solved the question, and in a very, very short time, another guy
That is a good point.
Yeah.
That is a good point.
say, I solved the problem, he solved it.
Right. Actually, in that scenario, just like what Yongjun introduced just now, that create two different branches. Because everybody else, whoever accept the first information, they will think it is truth. So then the entire network will create two branches. But what is unlikely is the next two people solve the problem simultaneously, and then the two branch grows in the same length simultaneously. Because there is a policy in Bitcoin, so whichever branch is longer, you switch to the long branch, and you just copy the information in the older branch to the new branch.
And if both have same
Well, basically, we make a very good hash function to make that last likely. But even if it's last likely, there's still a kind of like 1/1 million to happen. But it's unlikely for 1/1 million to happen twice, right? Right. That's basically the level of confident things.
I have said emphasize the difficulty or the time needed to compute the number, the guess number. Actually, is decreasing. So someone is going to adjust the difficulty level of the computational game.
Well, I would say the difficulty is increasing.
The difficulty is
Yeah, so,
Right.
so someone is changing the hashing function all the time.
No.
No, you just need to
Change the
change the threshold.
Right.
Oh. So
You can write a for
probability.
So the result of the hash function, you can think of it as a number. So we want to find a noun such that the result is less than something, say 1,000, 2,000.
So there's a space of
Yes.
numbers and
The solution space, you can shrink it.
Let's shrink the interval.
If you shrink it, then the puzzle becomes more difficult. we enlarge the solution space, it becomes more easy.
So how many numbers? How big is the space?
Well, I don't know the exact number right now.
But it seems
Right.
strange, right? On one hand, it gets the money becomes difficult, but on the other hand, you can get less reward, right? The Bitcoin becomes less.
Actually, that is an economic problem because they want to make sure that Bitcoin keep a certain value
Yes.
theoretically. So that is because the designer of Bitcoin, I think, is a Japanese scientist. So while he's designing the policy of Bitcoin, he was working with an economist to decide for example, why he decided to decrease the number every 4 years. 4 years is not a random number. It is economically proved, I think.
Okay.
So we will have a discussion later if you still have some more questions. Let me finish my talk and I will give you some pointer. So this is cutting line. Before this cutting line, the about thing is the introduction from a programmer's or from a coder from a IT lover's view. So firstly, there is a general introduction video. You can find it on YouTube, and I think this is quite gentle, even more gentle than that. Then the second thing, the second slide is basically the homepage of Ethereum Lab, and you can find whatever you want about the introduction of programming in Ethereum, the introduction of smart contract, and basically a lot of example codes and basically the virtual machine right in their homepage. And then, oh, by the way, I just said that I attend workshop, and you can find the workshop notes. Basically, that is also a very super informative workshop. And the presentation notes you can find on these two addresses. And Andrew Miller is mainly talk about security programming things when you try to design smart contract. So if you want to check out Ethereum project and Argo project, I mentioned somebody tried to solve the non-deterministic smart contract problem using principal component analysis. I know you're interested. Anyway, so you can check out his project page. So you can also check out the .bit project if you know what DNS is, you know what GoDaddy is. Anyway, you can check out this project because this project trying to do a decentralized DNS server using the blockchain technology, which is also quite ambitious and I would say has a lot of potentials. And for research for I would say guru or PhD or some kind of youth, I find to root paper of the entire topic, and you can find the grandfather of the smart contract, possibly the grandfather of grandfather. Anyway, of smart contract. And you can dive alongside the entire publication list, and you can see what's happening actually. And actually, we should give a latest publication. I think that is worth reading too. And I think that's the end for my talk.
Okay, so last but not least, hi, cousin, can you show our open international page?
Oh,
yeah. Because there are many new faces tonight, and yes. Okay, so we are open international, and we will have a weekly meetup like this. But this is the last event of this term, and we will come back next time. Okay, so if you like us, just like us and join our group in Facebook. Okay.
Right. Oh, by the way, I have a closing word indeed. Anyway, so I just talked about financial technology. Actually, it's not technology. It's not technology to help bank. So basically, knowing all those things cannot get you into UBS. But financial technology is kind of a technology that is so ambitious to take over the bank. So technology actually not necessarily give you a lot of money, but technology help you to create things. Just like the one who created this world does not have so many money, but he has the entire world. Anyway, so that is the end of my presentation. Thank you. We can have a discussion next week.